Hi, today we'll be presenting a project on transparent keyboard for the course EC561 hardware software design of embedded systems. And I will be Venkatapon Ramasai Bharadwaj, and Yasit will be joining us in the later slides of the presentation. So let's get into it. So why a transparent keyboard? Why do we have to go for a new design when we already have a lot of keyboards in the market? Although the USB keyboards are sold at say $11, $12, but why do we or why do we want to shift for a new design in the keyboard? Because as we already know, I mean, as we have seen, a lot of keyboards are mechanical, and there hasn't been a lot of aesthetic design change in the keyboards. There just has been change in the key press and the distance the keys go into, and the mechanical feedback. That's most of the design change that we have seen, but not a lot of aesthetic appeal that has been seen in the keyboard. So we just wanted to go different, and we wanted to provide a different keyboard, and we wanted to produce a aesthetic appeal giving transparent keyboard. So that's and also that we wanted to build the keyboard as low as possible in the cost, because there are, as we'll see now, there have been already a lot of models that have been released with a very good aesthetic appeal, and the one on the right hand side top of the screen is the laser projection keyboard, which works on infrared sensing, and it uses laser projection onto the surfaces. And but one thing that laser projection keyboards need is a stable surface and plain surface to deal with, and to project and to sense what is um, being detected. And the cost of that product is around say $40 in the sites that we usually buy stuff. And the one to the left bottom of the screen is the Bastron glass keyboard. Bastron is a Chinese company which offers glass keyboard at around $100, which is pretty nice from the looks of it. And it actually has mouse capability and swipe gestures as well, but kind of costly, $100. Come on. So, and there's another model of the transparent keyboard here on the right hand bottom of the screen, which is made by the company called Brookstone, which has the same similar functions. Both of these are offered in wired and wireless supports and varying costs, and this one here, right here, is offered at $90, and yeah, that's about it. So we just wanted to make the product as low as possible, close to the projection keyboard, and the estimates of the our keyboard are say around $60, and that's the best we could do. Yeah, here comes the design of our project. It's based on infrared sensing, and the emitters and the sensors are arranged in the periphery of the frame that we actually can see in the figure over here. The emitters are placed on to the left and the bottom of the frame, and this is a top view, of course. And the sensors are placed on top and the right side of the frame. It's not mandatory to place it here and here, but it's a basic thumb rule that obviously have to follow, is that the emitters and the sensor should be in the opposite direction. So that's about it. And these emitters and sensors are connected to a Teensy micro controller, Teensy, which is a special version, which we'll get to it later. Um, so here's the keyboard layout that we could achieve. We actually wanted to make it a 12 by 4 matrix and have all the functions included in it, but we could successfully do a 7 by 4 matrix with 28 inputs, As we can see, there's like alphabets A, B, C up until D, the 26 alphabets, and the two special functions. One is space, and the other is a special, which, when pressed, and just a single press would do, and then probably, and you'll be getting the numerics and the symbols that are shown here. So we could do 54 alphanumeric symbols with this, and so now we'll see what are the components that we've used. The one that is being displayed here on to the right top of the screen is the Teensy 3.6 version. And why not Raspberry Pi? Since like Raspberry Pi is all cool and it has a lot of capabilities, but it's not that required in our project. And also Raspberry Pi does not have a USB out port. It only has a USB input port, and Teensy has both the USB input and the output ports, which can be seen here. This is the output port, and this is the input port. This is connected to the computer, and then you can connect the output port as well to this. And here is the IR 940 nanometer wavelength sensor that emitter that we used in our project. And here is the sensor that we used onto the right bottom of the screen, which is a TSOP 38238IR receiver sensor. The 38 here indicates that it is tuned to 38 kilohertz, and which we'll see why that is important for us. The IR emitters and receivers are arranged in a rectangular fashion, as we already know, as we have seen earlier, and the IR emitters have been tweaked to emit signals at 38 kilohertz so that the tuned sensors could detect it properly. And whenever the beam is broken or it is disrupted, a positive edge change triggers the key press. And the Teensy has a library which sends all the alphanumeric symbols to the computer. So that's how the working of the prototype works. And now Yasit will be explaining the later parts of the presentation.
As told earlier by Bharadwaj, we have designed a 7 by 4 matrix. So what we'll be having is 7 emitters in the vertical side and 4 emitters in the horizontal side, along with the respective sensors. And the basic algorithm involves here is uh, setting two flags called H and V, which represent whether a horizontal IR light has been blocked or a vertical light has been blocked. Initially, the emitters are initiated with a 38 kilohertz pulse because the sensor is designed to demodulate the 38 kilohertz frequency. So, as the emitter emits the pulse and the sensor receives it, that is an active low sensor. So, whenever it's receiving the IR light, the output is 0, and whenever it's not receiving the IR light, the output is 1. So, as you can see in the right hand side, this code has been written in such a way that whenever a finger is dropped, what we can logically think of is the IR light gets blocked, and because of this the output at the sensor changes to 1. So we detect a change from 0 to 1. So this code ensures that only a 0 to 1 change is detected, not some other change. Like we want to set the flag only when finger is placed, not when it is removed. So the same way the flag setting is done even for the vertical sensors. And there are many if statements. So based on the location of the finger press, like suppose H can take the values from 1 to 4 because there are 4 horizontal emitters, or we can even say sensors, and there are 7 vertical sensors. So based on where the light is getting blocked, we were able to write a CPP code which has been uploaded into the Teensy board. And here you can see there is even a special flag, as Bhardwaj has mentioned. This special flag ensures that a different key output is displayed when the special key has been pressed, or else the normal alphabet gets displayed. So these two are the main major blocks of our code. And now I'll be showing you the demonstration. As you can see, uh, there there is notepad which records the key presses. There is a USB wire going into the teensy board, and here is our setup. So now what I am going to show you is the all the alphabets in a sequence. Like you can see A, C, D, E, and so there are 7 alphabets in the first row, and similarly the next 7 alphabets. The As you can see, like the alphabet is only appearing when I drop my finger down, not when I am removing it up. So as you can see, all the alphabets are coming up properly. And now I'll show you the space symbol. This is the space functionality, and I press space. So there. Now continue the remaining alphabets. This ends the alphabets. Now this is going to the special key here. So this should trigger now the uh, other set of characters. As you can see, this is the ones which were displaying ABCD are now displaying 2 3 4 5 6 7, and the same continues for the bottom row. uh, as you can clearly see, only when I drop the finger the symbol gets displayed. And now I'm again typing the space. So as you can see, there is space has occurred. And yes, this concludes all the remaining alphabets. So this was for our demonstration. So what we are left now is improvements what we thought could be made more. So now we are only sending a 38 kilohertz pulse from the emitters, but it would be very better if we were able to send encoded signals, because like the the signal being edited by the emitter in the second row should not be received by the sensor in the third row. So encoding takes would have taken care of that. But uh, and it would have also been good if there were the horizontal and the vertical beams were not in the same plane, because this prevents interference. And we initially proposed that the material would be glass fiber, which would make it completely transparent. But because of the fear of reflections and poor insulation, that is, the IR light, not able to control the IR light in the desired direction, we had to go to the thin balsa wood type of material. And as I've said about poor insulation or reflections, this could have been taken care of had we used tin oxide layering on the glass. And because there would be slits, and this would have allowed the IR light to pass properly. And one more major improvement we could have worked upon is the implementation of combination of 2 or 3 keys. So yeah, thank you for the opportunity you have given us to do the project.